Hi there. Okay, I want to do a quick little lesson on Newton's third law. So if you can take out your booklet, and I think it's page 18. I'm hoping it's page 18 in your booklet, but if you can come and find that, that would be great. Okay, so we've done Newton's first law, Newton's second law, and this is the last one. So Newton's third law says that for every action there is an equal and opposite reaction. Okay, so hopefully you've watched the Brain Pop videos on Newton's laws. It gives some good examples about this. And the big thing is that forces always come in pairs. Okay, so there's always an action force. Okay, and that's the force that is causing the situation. And then there's always a reaction force. And that's the force that responds to the action force. Okay, these forces are always equal in size, meaning like in the amount of force, okay, but opposite in the direction. Okay, so let's take a look at a couple examples. Okay, the first one says a baseball is moving towards the glove. Think about the forces involved when the ball is being caught. Okay, so you can see the little arrow here. It shows that the ball is going towards the glove. What is the action force? Okay, so I would say the ball pushes against the glove. Okay, so that is our action force. That is the force that is causing the situation. The ball pushes against the glove. So one object, the second object. So we're talking about the two objects that are involved. What's the reaction force? Turn it around. Okay, reaction force, the glove pushes back on the ball. It's that simple. Okay, yeah, your hand is gonna burn. Yeah, you might fall over because the pitch was so hard, but this is the action and reaction force. It's only between the two immediate objects that are touching. Okay, let's try another one. You jump on a diving board. Think about the forces involved when the person is in contact with the diving board. Okay, so we can see right away we have one arrow that's going this way and one arrow that's going this way. Okay, so what is the action force here? Okay, you push down on the board. Right on. Okay, so you are pushing down on the board. So you are interacting with the board. Okay, you're causing the situation, and the reaction force the board pushes back on you. That's it. Okay, it's literally that simple. So whenever we're having an action or a reaction force, okay, think about what are the actual two objects that are touching, and then are they moving towards each other or against each other? Okay, turn the page. Okay, it says think about this. What happens if the masses of two different objects are different? Okay, so remember in Newton's second law, we use the equation F equals m times a, so force equals mass times acceleration. There's my little vector. Okay, it's still applicable here too. Okay, so the question says, why does a cannonball move so fast compared to the cannon? So I don't know if any of you have ever been to a circus or seen a video online where they shoot someone out of a cannon, but notice how the person moves and the actual cannon does not move at all. Why is that? Okay, so let's figure it out. So we're going to have to keep track of two things here. Okay, so we're going to have our cannon and our cannonball. Okay, so it says, let F, the force of 500 newtons, represent both the action and reaction forces, right? Because they have to be equal. Okay, so equal, both have 500 newtons. The mass of the cannonball is 25 kilograms, and the mass of the cannon is 250 kilograms. What is the acceleration? Okay, so we have our person who's going to fly out of the cannon, and then we have our cannon. Okay, they're going in opposite directions. Okay, they're both 500 newtons. Okay, but he's going to go this way, and the cannon's going to go that way. Okay, and the mass of the cannon is 250 kilograms, and the mass of the person is 25 kilograms. Oh, the mass of the cannon. Okay, so let's use our equation. Okay, so we're going to do it twice. Force equals mass times acceleration. Okay, force equals mass times acceleration. Okay, so we're trying to solve for acceleration. So we want this. So let's just rearrange our equation. We're going to move mass over to the other side. So we divide both sides by mass. So we get acceleration equals force divided by mass. Okay, I'll do the same thing over here. It's much easier to do that now rather than later. Okay, so and now let's plug in what we know. So for our cannon, that is this side, our force is 500 newtons divided by 250 kilograms. Okay, and over here, for acceleration, our force is 500 newtons, that doesn't change, divided by 25 kilograms. Okay, so take out your calculator and figure out what that is. 500 divided by 250, what does that get you? Right, so your acceleration is 0.5, and the units for acceleration are meters per second squared. And which direction are we going? Backwards, right? The cannon is going backwards. Now, what about the cannonball? Okay, take your calculator. 500 divided by 25, what do you get? Right on. 20 meters per second squared going forward, right? Opposite directions. Oh, excuse me. Equal forces. Okay, so just by doing the math, we can tell that this is true, right? Equal force, opposite direction, it holds true. The difference is because their masses aren't the same. That's why the cannonball, you don't see the cannonball move very much, but the cannon, or sorry, you don't see the cannon move very much, but the cannonball moves a lot, okay? So that in a nutshell is Newton's third law and how to use math to support it. And I have all these awesome activities that I would do with you, and I'm just going to kind of go over them quickly. So in class we have all these spring scales, and they literally let you feel what 10 newtons feels like, because we can talk about like, oh, that's 2 newtons worth or 5 newtons, but to actually feel how much 10 newtons is worth is really interesting, and it's not very much at all. So if you like hook your fingers together and just pull gently, that's about 10 newtons. It doesn't take very much, okay? So we would take the scales and we'd each hook our scales together and we'd pull apart and we'd see if we could possibly get a different reading. Like if I hooked mine to Braden's, could I have 7 newtons and he have 2 newtons? Well, no. No matter how much we try, we'd always have the exact same amount of newtons, okay? And if we hook them together, my force is this way and the other person's force is that way, okay? Opposite force, and it'll always have the same reading, okay? And I like this. Do you both feel a force when only one person is pulling? Yes, of course, right? If you bump into somebody in the hallway, do you feel a force? Yes. If someone bumps into you in the hallway, do you feel the force? Yes. Both people always feel the force. Okay? And does it matter who's pulling on the scale? No, doesn't matter at all. Okay? The other activity we do is we have these dynamic carts, and they're literally just little carts like this on wheels, and then they have these big metal loops on the front. Okay? And we take them and we ram them into the wall, literally. And we'll put some will have leave empty, and then some will put masses on them. And so all we're doing is testing out if we increase the mass, what happens to our acceleration? If we decrease the mass, what happens to our acceleration? If we increase our force, what happens? Okay, and so it's really interesting to watch them kind of spring back and forth and follow through on this law. I'll see if I can find a demo video of that. Okay. Okay, so another station is just taking a ball, like take a tennis ball, take a soccer ball, volleyball, whatever, and bounce it on the floor. Okay, the interaction between the ball and the earth or the ground is what we're talking about here. Okay, so any ball that you push, it says where is the force coming from? Okay, so say you took a tennis ball and it hits the ground, but the ball moved back upward. So there must have been a force making the ball move upward. Where is that from? Well, the earth is pushing back on the ball. If you drop the tennis ball with a greater force, does it go higher or lower than before? It'll go higher, right? More force pushing back means more acceleration. Okay, mass stays the same. And then the other one we have here is we have a balloon taped to a straw and then on a string. Now, if you have a balloon and string at home and a straw, this is actually kind of neat. Just tie the string to something a little bit higher up. Blow up your balloon, tape your balloon to the straw, feed your straw through your string through the straw, but don't tie the balloon. Okay, so once you filled it up with the string through it, when you let go, watch what happens to the balloon. Okay, your balloon is going to move this way, but the air inside the balloon is moving out. Okay, equal and opposite reactions. Okay, and that's it for Newton's third law. What I would like you to do now is try and demonstrate, make a small video of Newton's third law at work. Okay, go to it.